So in this final part on bounded sets in R, we will describe certain important subsets of R which are called the intervals, and then we will prove the existence of the nth root, positive nth root of a positive real number, and finally we will show that the set of rational numbers is not order complete in itself. So first of all, what are intervals? Suppose you take any two real numbers a and b, then you can define four types of special subsets of R which are called bounded intervals in R. So notice the notation here is that if I take third bracket AB, that means all real numbers which are strictly uh, greater than or equal to A and less than or equal to B. In the last lecture, we saw that between any two real numbers, there are infinitely many rational numbers and also infinitely many irrational numbers. So this subset, third bracket AB, has infinitely many elements and it is called a closed interval. This closedness will be described in a later lecture. Why this terminology? And if we, instead of the third bracket, if we take the notation first bracket A comma B first bracket closure, then this would mean that it consists of all real numbers which are strictly greater than A and strictly less than B. So again, this is an infinite set. This is called an open interval. So when we leave out this A and B are called the end points of the interval. So if we leave out the end point, we will describe that by taking a first bracket, and if we include the end point, that is depicted by taking notation is that you take the third bracket. So what you can do is, so first what you did was you took both A and B as elements of the set. That is called the closed interval. For the open interval, A and B are both left out. You look at all real numbers which are strictly between A and B. If you include A in the set, that is, if you start with all x greater than equal to A but do not include B, then that will be denoted by third bracket A, B first bracket. So all x greater than equal to A less than B. And similarly, you can get the other one also, where you leave out A but include B. So you look at all x such that x is greater than A and less than or equal to B. So you get these four types of intervals which have endpoints A and B. First interval is called closed interval, second one is called open interval, and third and fourth are called either semi-open or semi-closed intervals. It is not so depends on you actually as to which one you want to call semi-open and which one you want to call semi-closed. It doesn't really matter. So now what you do is that instead of bounding it on both sides, you just bound on one side. So what does that mean? That suppose I take any A in R, and if I look at the collection of all real numbers which are greater than equal to A, so on the line, on the real line, you have this point corresponding to A. You are looking at all points in R which are greater than equal to A. So this you depict by, since you are including A here, you have a third bracket A comma, use infinity as a symbol, which means just this set, that all x greater than equal to A. Similarly, if you want all x less than or equal to A, then you depict that as minus infinity to A third bracket on the A side, that is you want to include A here. So you have these two, and you also have as in the previous bounded intervals, you can leave out the A also. So you can look at open interval A infinity, where you are considering all real numbers which are strictly greater than A, and also you can consider minus infinity to A, where you are considering all real numbers which are less than A. So this is one example where you are using infinity to describe a certain notion. Infinity is not a number here, so there is no question of having a third bracket on the infinity side or minus infinity side. It just means this: you have the set of all real numbers which are greater than equal to A. This whole set is written in a short form like this, if you would like to think of it. And similarly, all these three. These are called unbounded intervals of R, and the previous four intervals were called bounded intervals. So naturally, you know what is the meaning of bounded sets. So you would like to relate that these are actually bounded sets and the other ones are unbounded sets, so that we will make clear quickly. And notice that if you have the real line, any real number is actually greater than minus infinity and less than infinity. That is how we want to imagine. So we use the symbol minus infinity to infinity. See, what I said was that any real number is greater than minus infinity and less than infinity. That is true in the extended real number system. But since we have that notion in mind, we are using the notation here that the real line or the set of real numbers is written as open first bracket minus infinity comma infinity first bracket closed. So I think I am able to explain it to you that here we have that logical interpretation in mind, and therefore we are using the notation this to express R. Okay. Again, all these sets are infinite sets that you can realize, because say for example, if I show that this is infinite, then this is automatically infinite. This will at least contain the number a plus 1 and also the number a plus 2. So there are infinitely many real numbers between a plus 1 and a plus 2. So this will contain infinitely many real numbers. Similarly, if you look at this set minus infinity to a, it will at least contain a minus 1 and also a minus 2, and there are infinitely many real numbers between a minus 2 and a minus 1. So minus infinity to a also has infinitely many numbers. So since these two are infinite sets, this is automatically these two are also infinite sets. So all the intervals are at least infinite sets. This you should keep in mind. Don't get confused. Generally, when I say that, suppose I look at the close interval 1 comma 2, then the tendency is to think say that 1 is there, 2 is there, but nothing else is there. That confusion should not arise, because we have already learned many things. So there are many fractions between 1 and 2, all of them are included, as well as there are many irrational numbers between 1 and 2 that are also included. So all these sets are infinite sets. Four of them are called bounded intervals, four of them are called unbounded intervals. So let us just understand why. Suppose I take any two real numbers a and b, where a is less than b, and suppose capital I is one of these four, that is open interval AB, semi-open interval AB, semi-open interval or semi-closed interval if you like AB, and closed interval AB. Then I want to say that this is a bounded interval. So why would that be true? If you take any x in I, then this is true for any of these. See, in the first case, x is strictly greater than a and x is strictly less than b, but that is included in this inequality. So the strict inequality is included in this inequality. Similarly, if you are here, then it would be a less than x less than or equal to b, so that is included in this inequality. Similarly for this one, and also the final one, close interval AB, if x belongs to I, then A is less than equal to x less than equal to B. So in any case, this statement is true for any x in either of these four intervals. Therefore, A has to be a lower bound of I and B is an upper bound of I. So therefore, I is a bounded set. Now what we will justify is that whatever be the set, any of these four, A is going to be the infimum and B is going to be the supremum. So in the case of the last one, the infimum and supremum will be elements of A, or elements of the interval, but in the first case, the infimum and supremum will not belong to the interval. And similarly, you can argue for these two. So let us see why this is true. The argument is quite simple actually. So I have A is a lower bound of I. I want to say that A is the greatest lower bound of I. So I increase A a little bit and show that it is no longer a lower bound. So you choose any epsilon greater than 0. Then uh, let us look at this picture. So what you do is that this epsilon could be huge, it could just surpass B also. So if it were such that A plus epsilon becomes greater than B, then the whole of the line segment between A and B would be between A and A plus epsilon. So in particular, your A plus epsilon will no longer be a lower bound of I. I hope I have explained it, that if you take any epsilon greater than 0, then A plus epsilon could be any number which is on the real line. It may be greater than B also. If it is greater than B, then automatically every element in between A and B is going to be less than A plus epsilon. So in that case, your A plus epsilon does not have any chance of being a lower bound of I. So therefore, that part is trivial. So I have ignored that part. What I have done is that suppose I take an epsilon greater than 0, so that A plus epsilon is less than B in the figure. Okay, so if A plus epsilon is less than B, I want to still claim that A plus epsilon cannot be a lower bound of the interval I. Why is that true? Because A is a real number, A plus epsilon is a real number, so there will be many real numbers strictly between A and A plus epsilon. If there are, if you take any real number strictly between A and A plus epsilon, then by this choice of A plus epsilon, it will be less than B and it will be greater than A. So it will belong to the interval I, whatever your I be. I has these four choices. If I is open interval AB or this one or this one or the closed interval AB. In any case, if you have such a situation, since there are infinitely many real numbers between A and A plus epsilon, all these numbers will be less than A plus epsilon. So A plus epsilon will no longer be a lower bound. So if you increase A little bit, then that particular number cannot be a lower bound of the interval. Therefore, A is the greatest lower bound possible and hence A is the infimum of capital I. This is what we are saying. Now if you want to make it analytically precise, what you do is you look at the distance between b and a, b minus a, and look at epsilon, then look at the minimum of these two. Then this is going to be a real number, and this real number is going to be positive because epsilon is positive, b minus a is positive. So the minimum of these two is a positive number. So between 0 and that positive number there are infinitely many real numbers. Choose any such real number delta. Then what happens is that a is less than a plus delta because delta is positive, and since delta is less than b minus a, so a plus delta is less than b. Therefore, a plus delta belongs to I, and also a plus delta will be less than a plus epsilon because delta is less than epsilon. So therefore, what have you got? You have, if you increase a by a plus epsilon, then you will be able to get an element of the interval which is less than a plus epsilon. Hence, a plus epsilon will not be a lower bound of the interval, and hence little a is the greatest lower bound. I hope I have made it clear. Similarly, this argument, this b minus epsilon could be small enough that it goes to the left of a, but even if it doesn't go there, same delta which you chose here will work out here also, because now you see that if you look at b minus delta, that is going to be greater than a. Why? Because delta is less than b minus a. So b minus delta is greater than a, and obviously b minus delta is less than b because delta is a positive number. So b minus delta is in the interval because it is between a and b. So whatever be your expression of the interval, whether you include a or not, whether you include b or not, at least a less than b, this whole portion is going to be a subset of I. That is, this first one, open interval AB, is a subset of all of them. So therefore, if you can find a point between, in this set, then that particular point is going to belong to the interval I. That is what the argument is all about. So B minus delta is in I. Also, delta is less than epsilon, so minus delta is greater than minus epsilon. So B minus delta is greater than B minus epsilon. So what have you shown? You have shown that if you decrease B by an amount epsilon, if you take the number B minus epsilon, then it can be no longer an upper bound. There is an element of I which is greater than that. So B minus epsilon is not an upper bound of the interval. Therefore, B is the least upper bound of the interval. Therefore, supremum I is B. So, whatever be your choice of I, any of these four, infimum of I will always be A, and supremum of I will always be B. So these are examples of bounded intervals. Okay, what happens in the next four cases? You have either A infinity or this interval where a is included, all x such that x greater than a, or all x such that x greater than equal to a. So realize that it is clearly unbounded above. If you take any element x here which is greater than a, then x plus 1 is automatically greater than x. So none of the x which are greater than or equal to a is going to be an upper bound, so it is unbounded above. What about the lower bound? As before, you can see that a is going to be a lower bound by definition. This means all x greater than a, and this means all x greater than equal to a. So a is going to be a lower bound of I. Again, as before, a is going to be the infimum of I. So this is bounded below, and we know that if it is bounded below, it should have an infimum, and that infimum is in fact going to be a. In this particular case, the infimum belongs to the set. In this case, the infimum does not belong to the set. So what is your proof? Your proof is again the same, that you increase your A by a small amount, suppose epsilon, then you choose your delta to be between 0 and epsilon. Since epsilon is positive, there are infinitely many real numbers between 0 and epsilon. Choose any one. Then what do you get? You get A is less than A plus delta, because delta is positive. Hence A plus delta is a element of the interval. Not only that, since delta is less than epsilon, so A plus delta is less than A plus epsilon. So what did you get? You got an element of the interval which is less than A plus epsilon. So A plus epsilon can no longer be a lower bound. Therefore, if you increase A by a amounts, however small, that will no longer be a lower bound of the given set. Therefore, A is the greatest lower bound. That is what you have proved, that infimum I is equal to little a in both these cases. Similarly, now I think you have got the hang of the argument that if I take intervals of this type, minus infinity to b or minus infinity to b closed, this means all x real numbers which are less than b, and these are all real numbers which are less than or equal to b, then these two sets are clearly unbounded below. Because if you take any x which is less than b, then x minus 1 will be automatically less than x less than b. So therefore you will not be able to get a lower bound. What about the upper bound? Every x in either this or this is less than b. It is less than b here, and here it is less than or equal to b. So b is going to be an upper bound. And as before, you can show that b is the least upper bound. So how do you show? You just increase b by a little bit. So suppose you take any epsilon greater than 0. So just imagine your line here. You have b and you have increased it to some b plus epsilon. Then you I'm sorry, I wanted to say that b is the least upper bound, so I want to decrease. So if you decrease b by epsilon, you'll get a b minus epsilon on the left hand side of b. Then there are infinitely many real numbers between b minus epsilon and b, which will mean that b is the supremum. So carefully, if you want to write down, again you take any delta between 0 and epsilon, then look at the number b minus delta. Since delta is positive, b minus delta is less than b, which will imply that b minus delta belongs to I. Whether I is this or this, it doesn't matter. And also, since delta is less than epsilon, b minus delta is greater than b minus epsilon, because minus delta will be greater than minus epsilon. Therefore, if you decrease b by a small amount, or however small, it will no longer be an upper bound of the interval. Therefore, b has to be the least upper bound. Therefore, supremum of I is equal to b, which is, if you just stare at it, it is quite clear. So what have we got? These type of intervals are not bounded intervals. They are, here it is bounded below but not bounded above. Here it is bounded above but not bounded below, and you are getting the suitable supremum infimum as you expect. Okay, and these four were all bounded intervals. Very good. Next, I am going to prove a result which is very, very important, even though it is not part of your syllabus. But since we are doing mathematics in a leisurely fashion here, I am just going to discuss a few results which are beyond syllabus. So it is not in the syllabus in the sense that you are obviously expected to know the result, but you are not expected to know the proof of the result at this first case. But it is a good exercise to go through this proof so that you get the full hang of supremum and infimum. So let us see what is our result. This is something which we use you have been using it from your middle school itself, I think, that if you take any positive x and if you take any positive integer n, then you will be able to get a positive real number y, so that y to the power n is equal to x, and this y is unique. That is, there is the existence of the nth root of x, and that nth root of x is positive nth root of x is unique. This is a very, very important result. We will denote this, since it is unique. We can give it a notation, and that notation is x to the power 1 by n. Notice we have been very careful. It has to be a positive real number. So because you already have this type of ideas, that if you take, say for example, x equal to -1, and if you assume n is equal to 2, then there will be a problem. So in general, we cannot give this result for arbitrary real numbers. For positive real number, there is a unique positive nth root. That is what is the result is saying. So let us just prove this. First of all, uniqueness is not difficult, because if you suppose that y is less than z, then you just and both are greater than 0, of course, then you multiply this by y. What do you get? You get y squared is less than y into z. Now y into z is going to be less than z square, because y is less than z, right? So once you have y less than z, y squared will also be less than z squared. Similarly, again you multiply by y, then you will get y cube is less than y squared z, and that will be, y z squared, right? So you have y square is less than z square, multiply by y, you will get uh, y cube is less than y into z squared, and that will be less than z cube. So very simple algebra is telling you that if you take any two numbers y and z, positive numbers, if y is less than z, then y to the power n is less than z to the power n for any positive integer n. So therefore, if you get, you don't know whether you will get, but suppose you get y to the power n is equal to x, then no other z will satisfy the property that z to the power n is also equal to x. Take any other z, if it is greater than y, then z to the power n has to be greater than x, and if you take any w which is less than y, then w to the power n has to be less than x. So there will be exactly one y for which y to the power n is equal to x, because of this implication. Okay, so how do you construct this? How do you find this y? So what you do is you just take all t, so that t to the power n is less than x, and then uh, of all these t's you will get the supremum. That supremum is going to be the solution to this equation. So let us do it slowly. Suppose I take a set S which consists of all positive real numbers, so that t to the power n is less than x. Then first of all, I want to show that this set is at least non-empty. So why is this non-empty? There will be some hardcore algebra in this proof. So you can look at this real number, x divided by x plus 1. So call this t0. So clearly x is positive. This is our assumption. So t0 is going to be greater than 0. And look at the fraction. It is x divided by x plus 1. So t0 is going to be less than 1. So t0 is a real number between 0 and 1. Very good. So again you do similar type of thing which I was discussing here, that you multiply this inequality by t0 again, you will get t0 squared is less than t naught. Then you again multiply by t0, you will get t0 cube is less than t0 squared, is that way it will be less than t naught, and so on. So you will get t0 to the power n is less than t0 for all positive integers n. So in particular for this fixed n which we have here, we will get t0 to the power n is less than t0. And what can you say about t0? T0 is strictly less than x, because x plus 1 is greater than 1. X is positive, so x plus 1 is greater than 1. Therefore 1 by x plus 1 is less than 1. Therefore x by x plus 1 is less than x. So you have got a t0 which is a positive real number whose nth power is less than x. So therefore t0 is an element of S. So at least S is non-empty. You will show that S is also bounded above. Okay. So if you take t to be greater than 1 plus x, then it is automatically positive. Then I want to claim that t to the power n is greater than t. Why is that true? Because t is greater than 1 plus x means t is greater than 1. So since t is greater than 1, t squared is greater than t, multiply by t. So t squared is, and t is positive clearly because t is greater than 1 plus x. So t is greater than 1, so t is positive. Multiply by t, you will get t squared is greater than t. Again multiply by t, you will get t cube is greater than t square, and that was seen to be greater than t, and so on. You keep on doing it for n times. You will get that t to the power n is greater than t. I hope I am able to explain this part to you properly. So t to the power n is greater than t, and t is obviously greater than x because t is greater than 1 plus x. So what have you got? That t will not belong to S. Remember what was S? S was the collection of all positive real numbers for which t to the power n is less than x. So if I take any t greater than 1 plus x, then t will not belong to S. Means what? That if t has to belong to S, then t has to be less than or equal to 1 plus x. Right? Contrapositive of this statement. Since t greater than 1 plus x implies t does not belong to S. So if t belongs to S, then t has to be less than or equal to 1 plus x, which means that 1 plus x is an upper bound of S. So you have got a non-empty bounded above subset of the set of real numbers. Therefore, by its least upper bound property of real numbers, S will have a supremum. So y is equal to supremum S. Now what was S again? You go back. It is the collection of all positive real numbers for which t to the power n less than x. So its supremum, its upper bound at least, has to be positive. Since you are looking at positive numbers and then you are bounding it from the top, so it has to be a positive number. So first of all, y has to be greater than 0. Now what we will do is we will show that y to the power n is equal to x. That is what I said that we will be doing. So how to do that? We know by law of trichotomy then that y to the power n will be either equal to x or less than x or greater than x. So I will show that if y to the power n is less than x or greater than x, then we will arrive at a contradiction. For this, I told you there will be some hardcore algebra in this proof. So there is an identity, not a very difficult identity, but let us carefully see this. Look at b to the power n minus a to the power n. So you can take b minus a common from this. You will get b minus a into b to the power n minus 1 plus b to the power n minus 2a plus b to the power n minus 3a square plus etc. a to the power n minus 1. So why, from where will you get this formula? Just check that this formula is true. So how will you check? You multiply this thing in the bracket with b. What will you get? B to the power n plus b to the power n minus 1a plus etc. plus b to the plus b into a to the power n minus 1. Now multiply by minus a, and you will get minus ab to the power n minus 1, which will cancel out. b into this, and so on. So minus b to the power n minus 2a squared, and so on. So everything will cancel out except minus a to the power n. So anybody interested, please just take your pen and paper and work it out. It will be true. Now if I have assumed that a is less than b, so in this second bracket, if I replace every a by b, then your number will be strictly greater. And what are you going to get? See, the total sum of the exponents is n minus 1 for each of these terms. So here if you replace a by b, you will get b to the power n minus 2 into b. So again you will get b to the power n minus 1. Similarly, for b to the power n minus 2 a square, if you replace a by b, you will get b to the power n minus 1, and so on. So each of these terms will become b to the power n minus 1 if you replace a by b first of all. And notice how many terms are there. So how do you count it? Here it is ending at b to the power n minus 1, and it started with b to the power 0. So you have b to the power 0, b to the power 1, b to the power 2, and so on till b to the power n minus 1. So from 0, 1, 2, etc. till n minus 1, you are getting n elements. So in this bracket, there are n terms, and in each term, you are replacing a by b. So you are getting a number which is strictly greater than this. And what is that number? It is b minus a. This you have left unchanged, and n times b to the power n minus 1. This is what you are getting. This is our equation, that b to the power n minus a to the power n is less than b minus a into n b to the power n minus 1. So this is the algebra which is required, and using this we will prove that neither of this is true. So how are we going to prove it? So first of all, you assume that y to the power n is less than x, then we will be able to show that if y to the power n is less than x, then we will be able to increase y a little bit, so that y plus something to the power n will also be less than x. So why will that be a contradiction? Because if y to the power n less than x implies something, if you add it to y, that is also the nth power of that is also less than x, then you again recall what was your s. It meant the collection of all positive t's, such that t to the power n is less than x. So if y to the power n is less than x, I am claiming then that I will be able to add something to y, and still y plus h to the power n will remain less than x. So that will imply that y plus h will belong to s. But y was what? Y was the supremum of capital S. Then how can y plus h belong to S? Y plus h is a number which is greater than y, so it should not belong to S. But we will show that that will lead to the contradiction. Okay. So yeah, so we have seen this. So this is something odd. We will see why this is coming. So I want to claim that I will be able to increase it a little bit, so that y plus h to the power n is less than x. So how will I do that? I just look at y plus h to the power n minus y to the power n. Use this previous algebraic inequality which we proved here, and what we get is just y plus h minus y, so that is h into n times y plus h, that is your b to the power n minus 1, right? Remember that it is b to the power n minus a to the power n is less than b minus a into n times b to the power n minus 1. So here your b is y plus h and a is y. So b minus a is just h. You get a n, and then b to the power n minus 1. Very nice. So what have I done now is that suppose I choose my h to be less than 1. I want to just say that I will be able to get some h so that y plus h to the power n is less than x. So I have to make a choice of h. So first of all, you choose your h to be less than 1. So you will get what? You will get less than h n y plus 1 to the power n minus 1. So, something like this. What do you want? You want that y plus h to the power n should be less than x. This is what we want. So if I can somehow show that whatever ugly looking thing I have got here, that is less than x minus y to the power n, then I will be able to cancel out y to the power n on both sides, and I will get y plus h to the power n is less than x. So what is how can I do ensure that this is true? I have only one thing which I can change, and that is h. So if you assume that h is suitably small, then I will be able to write down this inequality. So look at this. What do you want? You want h should be less than x minus y to the power n divided by n into y plus 1 to the power n minus 1. So some sort of back calculation we are doing. So we want that h should be less than that. Therefore, we wanted h to be less than 1 here, and again we want h to be less than something here. So you want h to be less than 1 as well as this. So look at these two numbers. Both of these numbers are what? Positive, because we have assumed that y to the power n is less than x. So x minus y to the power n is positive, and the denominator is positive because y was positive. Remember, what is y? Y was the supremum of s. So since s consisted of positive real numbers, y was greater than 0. Therefore, your denominator is always positive and your numerator is positive by your assumption. So these two numbers in the second bracket, they are all both positive. Therefore, the minimum of that is a number which is greater than 0. Therefore, 0 and this number will have infinitely many real numbers between them. Choose any such h. Then you will get that y plus, for that h, you will get y plus h to the power n is less than x. Now, this is a contradiction because this, which I already mentioned, because y plus h will then belong to capital S, but y plus h is strictly greater than y, and y was an upper bound. So it is not possible. So what is not possible is this thing, that y to the power n less than x is not possible. Very good. Similarly, we will show that y to the power n greater than x is also not possible. So I am doing the same type of thing. So let me just see. I will just take a number which is smaller than y and show that if y to the power n is greater than x, then a number smaller than y will still be an upper bound of capital S. But that is a contradiction because y is the least upper bound. So what did we do? We chose k equal to this. This is again from back calculation. So y to the power n minus x divided by n into y to the power n minus 1. So since y to the power n is greater than x, numerator is positive, denominator is always positive. So k is a positive number, and also k is less than y. Why? So you just see what is happening. I want to say this is less than y. So I want to say that y to the power n minus x is less than n times y to the power n, right? So why is that true? Because y to the power n minus x is at least less than y to the power n. X is positive. So y to the power n minus x is less than y to the power n. So it is less than n times y to the power n. Therefore, k is less than y. Hopefully, I have been able to explain it to you, right? And so this number is here. Now you take any t greater than equal to y minus k. So y minus k is a positive number. So remember your previous I have written equation, but it was an inequality actually. So b to the power n minus a to the power n is less than b minus a into n times b to the power n minus 1. So I'm going to apply this inequality here. So now my b is y and a is t. So y to the power n minus t to the power n. This is going to be less than, first of all, I have, if I leave out just t, then there is a problem. So I, instead of t, I have just plugged in y minus k. So if t was greater than equal to y minus k, minus t is less than or equal to minus of y minus k. So minus t to the power n is going to be less than or equal to minus of y minus k to the power n. You can think of it like this, that since t is greater than equal to y minus k, t to the power n is greater than equal to y minus k whole to the power n. So minus of t to the power n is going to be less than or equal to minus of y minus k to the power n. So therefore this inequality is true. Now you apply 1 here. So your b is y and a is y minus k. So b minus a is just going to be k times n times b to the power n minus 1. So y to the power n minus 1. Right? So you get k n y to the power n minus 1, and see that this is just y to the power n minus x. So this is again, you realize that this is a back calculation, because what we wanted to show was that if y to the power n is greater than x, then I will be able to find a real number which is less than y and which is still an upper bound of s, which will be, which will lead to the contradiction because y was the least upper bound. So for that particular purpose, I want to decrease y by some k, and then I, what do I want, I keep writing it down, and from there I got this formula. It is not something which was just plucked from the sky or something like that. Okay, so here if you cancel out y to the power n on both sides, you get minus t to the power n is less than or equal to minus x, which means that t to the power n is greater than equal to x, right? So what does that mean? It means that t is not an element of s. What was capital S? Capital S consists of all positive real numbers for which the nth power would be less than x. So we are getting a t, so that t to the power n is greater than equal to x. Therefore, it is not an element of S. So what have you shown? You have shown that if t were greater than equal to y minus k, then t would not be in S. So again, the contrapositive statement says that if t belongs to S, then t has to be less than or equal to y minus k. Therefore, y minus k has to be an upper bound of S. But little y was the least upper bound. So anything smaller than that cannot be an upper bound. Y minus k is strictly less than y because k is positive. So this is a contradiction. From where did this contradiction come? It came from the assumption that y to the power n is greater than x. So this is also not true. So by doing some hardcore algebra, we have shown that y to the power n greater than x is not possible. Y to the power n less than x is also not possible. So the only possibility is y to the power n is equal to x. So if you just ignore the algebra part for the time being, you just notice that what have you done? You have just looked at, you wanted to show the existence of the positive nth root of a positive real number. So you started with all real numbers whose nth power is less than x, and started with all positive real numbers and just took the supremum of this, because it would keep on increasing if s is or rather say some w or something like that. If w is greater than t, then t to the power n is less than w to the power n. So if you look at t to the power n, this function is increasing in a sense. That is what we have written. So it will, and you are bounding it by x. So wherever the supremum arises, that is going to be equal to x. So you just get the philosophy of the result, and that is hidden here. Everything else is just a elaboration of that philosophy, that you know that when you look at the numbers y to the power n, as you keep increasing y to the power n will keep on increasing. So you look at all positive t, so that t to the power and consider the t to the power n's, they will increase with t, and you bound it by x. Assume that it is less than x. Then this set the, is going to the supremum of this set is going to give you the number, so that y to the power n is equal to x. I hope I am able to explain it to you. So you could have done it the other way round also. Now I don't want to confuse you, so I don't want to tell you what that should be. You could have chosen a suitable set and got the infimum of that, and that would have also given you a y, but this is sufficient for our understanding. This part is the philosophy, and the rest is then elaboration on that philosophy. Okay, so we will remember this result, that given any positive real number x, there is a unique positive nth root of x. So that is denoted by x to the power 1 by n. Okay, so the last thing which I want to mention in this lecture is that what would have happened if we just considered the set of rational numbers. So my statement is that Q is not order complete in itself. What does that mean? It means that it is possible to get a subset of Q which is non-empty, bounded above, but it does not have an upper bound in the set of rational numbers. It will of course have an upper bound in the set of real numbers. We know that the real numbers satisfy the least upper bound property. But if you just focus only on the set of rational numbers, then you would not get a least upper bound in Q. So that also gives you an argument in favor of extending the uh, rational numbers to the set of real numbers. Okay, so I'm using a notation here that this is not necessarily, I've put a greater than 0 as a superscript. This is not necessary. You could have put it as a subscript. So this is not standard, but I would use this one. You could have written it in any other fashion also. You could have written Q plus if you liked, as plus as a superscript or plus as a subscript. So there is no hard and fast rule. Any notation would work. I have chosen this, that Q greater than 0 means the set of all positive rational numbers. Now you define two sets in this, subsets of this. Take all positive rational numbers for which p squared is less than 2, call that set A, and take the set of all positive rational numbers so that p squared is greater than 2, call it B. We know that there is no solution to the equation x square equal to 2 in the set of rational numbers. So therefore, if you take any positive rational number, it will either be such that its square is less than 2 or its square is greater than 2. Therefore, the set of all positive rational numbers is going to be equal to A union B. No problems. Now notice that 1 belongs to A because 1 square is obviously less than 2. So A is non-empty, right? Again, if you take any little a in capital A and little b in capital B, then A square is less than 2 is less than B square. So if you take the square root of this, you will get, forget about the 2 in between, then you will get A less than B, right? we have already seen that there is a square root of a and there is a square root of b in the previous result, so there is no problem. Okay, so what have we seen? That if a belongs to capital A and little b belongs to capital B, then little a is automatically less than b. So if you take any little b in capital B, it is going to be greater than every element of capital A. Therefore, A is a bounded above subset. It is non-empty. So A is a bounded above subset of Q. Not only that, you have also seen that every element of B is an upper bound of capital A, right? So my ambition is that I will show that it will not have a supremum. It will not have a least upper bound. So how will we do this? This argument is from Rudin's book on principles of mathematical analysis, which I had mentioned a few lectures back, and I've just elaborated on that proof. Okay. So what do we do? This is a very smart trick, that take any positive rational number and define a new number. What is that? Q is equal to P minus P squared minus 2 divided by P plus 2. Okay, so now you do some calculation. What is Q squared minus 2? So Q was P minus P squared minus 2 divided by P plus 2. So you have to take the square of that minus 2. So just look at what is happening here. This is P square plus 2P. So P square will cancel out. So you are left out with 2P and minus here and minus here. So it becomes plus. So 2P plus 2 whole divided by P plus 2 whole square minus 2. Now you expand. In the denominator you will get P plus 2 whole squared, so that is there, and in the numerator here you will get 4P squared plus 8P plus 4, and here you'll get minus 2P squared. So let us do one by one. Here you are getting 4P squared and you are getting minus 2P squared from here, so you are left out with 2P squared. Then here if you expand you are getting 8P squared, and what will you get here? You'll get 2 times 4P. So you'll get a minus 8P again. So that minus 8P and 8P here will cancel out. And finally, you'll get a 4 here. And here you will get 4 into 2. So you'll get a minus 8. So you're left out with 4 minus 8. So minus 4. So in the numerator, you get 2 times P squared minus 2. And the denominator is P plus 2 whole squared. Very good. So if you look at any suppose that P belongs to A. So what did we do? We chose any real number, any rational number which is positive. Then it will either belong to A or it will belong to P. So first we say that suppose it belongs to A. So if it belongs to A, then P squared is less than 2. So what does that mean? That P square minus 2 is a negative number. Denominator here is always positive. Notice P is positive 2. If you add 2 to it, so it is positive. So P squared minus 2 will be positive if P belongs to A. I'm sorry, it will be negative. So minus of P squared minus 2 will be positive. That is what I'm trying to say. Therefore, if P belongs to A, then Q is greater than P. Is it okay? Because if P belongs to A, then P square minus 2 is less than 0. So P minus this negative number means you're adding a number to P. Actually, it becomes P plus something. So therefore, Q becomes greater than P. Not only that, if you look at this equation, Q squared minus 2 is equal to this. So denominator is always positive, 2 is a positive number, and in this bracket you get P squared minus 2 which is less than 0 because P was an element of A. Therefore you get Q squared minus 2 is also less than 0. That means Q squared is less than 2. So by the definition of A, Q will also belong to A. So what did you prove? You showed that if p is a positive rational number, then if p belongs to A, it is possible to get a q which is greater than p and which belongs to A. So any element of A cannot be an upper bound of A, because whatever element of A you take, you will be able to get an element of A which is greater than that element. So no element of A will be an upper bound of A. Now you have seen that what are the upper bounds of A? They have to be positive rational numbers, because A is a subset of positive rational numbers. So all the upper bounds of A in rationals have to be positive rational numbers. So they will belong either to A or B, because the set of positive rational numbers is equal to A union B. Now you have shown that no element of A is an upper bound of A. So every upper bound of the set capital A in the set of rational numbers has to belong to B. This much is clear. Very good. But again, you see that, so that is what I have mentioned here. Hence, if supremum A belongs to Q, then it must be an element of P. So now suppose that P belongs to B. Here, if P belongs to B, then P square minus 2 is positive. P square minus 2 is greater than 0. So therefore, what is Q? Q is P minus a positive number. So Q becomes less than P, first of all. And what happens here? Since P belongs to B, P squared minus 2 is greater than 0. So this whole thing is greater than 0. Therefore, Q squared minus 2 is greater than 0, which means that Q belongs to B. So that is what we are trying to say, that if P belongs to B, then Q is less than P and Q belongs to B. So B consists of all upper bounds of capital A, and it does not have a least element. Whatever be the element of B, take any P in B, you will be able to get a smaller element in B than that. There will be a Q which will be less than P and Q will belong to B. So no little p belonging to B can be the least upper bound of A. So therefore, you will not get the supremum in the set of rational numbers. That is what is meant by saying that Q is not order complete in itself. That is, it is possible to get a non-empty bounded above subset of rational numbers which will not have its supremum as a rational number. If you just look at the set, you can realize what is the supremum of this. It is precisely square root of 2, because p squared less than 2 means p is less than root 2. So what would be the supremum? The supremum would be root 2, and root 2 is not a rational. So the same argument from which we started is telling you this result. Okay, so hopefully I have been able to explain certain number of things to you. You have to remember what intervals are, and you have to remember the results which we proved, especially the existence of a positive nth root of a positive real number. Even if you don't uh, remember the proof in toto, it doesn't matter, but at least that result has to be remembered, because we will be using it later on. In the next lecture, I will be talking about the decimal expansion of real numbers. Okay, so maybe let us stop here.